So what we are going to be doing today is finishing off the section 8.1 on arc length. I went through and looked at some examples that we haven't, well, we may have covered some of them, but certainly we haven't covered them all. So here are 4 examples with the numbers I happen to have from 8.1. These are all arc lengths where the formula is in the form of y equals a function of x. And then there's fewer of these guys where you're trying to find the arc length when the function is written in terms of y, like x equals this guy. Essentially, these guys here are identical to these ones. The only difference is that the variable is going to be called y, and in this case, the variable is be called x. Couldn't they have called it t? Couldn't they have said w is t cubed plus t and do the same question, right? The variable name really doesn't change the gist of what you do. I think a second truism is the vast majority of these questions, don't they end up being perfect squares once you calculate the 1 plus derivative squared? So think of that as a very common theme, so that when you're doing some of these, not all of them, but when you're doing most of these, the algebra is going to come out in such a way that that's what you get. So these are our equations for a shape in the form of y equals f of x, and we're going to get its arc length. And this is the equivalent if it was x equals a function of y, and you also wanted to get its arc length. So now the reason I chose question 7, or at least a version of question 7, because you all know you get different ones, is that it wasn't written really in the format that it needs to be written. And what I mean by that is that this question isn't y equals, and it needs to be y equals. I mean, I could convert it into x equals, but that wouldn't be very easy. So I'm going to make sure that it's y equals. So we're going to use a method that is quite common for solving all sorts of situations. As long as you do it to both sides, it's okay rule. So that's what I'm going to do. So what should I do to both sides here? To get y squared, what should I do to both sides?
Divide by 36.
Okay. And what should I do now? To both sides, to get y.
Square root.
Square root. Yeah. Now, if you take the square root of this, it looks decidedly ugly. And it is. But that's not the version I'm going to keep. If you're finding the square root of 2 things multiplied, you can find the square root of each separately. So the square root of 1/36 is 1/6. And the square root of x squared minus 4. I check that number. Just out of curiosity, it looks wrong. No, that's a number. And if you take the square root of x squared minus 4 cubed, you get 3/2. Now that's the form that you really better write this guy in. If you leave it as a big ugly square look like that, you're going to go nowhere. I mean, the answer is just going to get uglier and uglier, and then you'll get lost in the weeds, right? You just won't be able to find your way out. So fractional powers are going to be your friend. Now, since this is a complicated one, won't we do the 1 plus derivative squared first before we even go near the integral? Now, I hope when you look at that, you're thinking chain rule. So you multiply by the power, and you reduce the power by 1. And then you, because it's a chain rule, what do you multiply after that? Because I'm not finished yet. Multiplied by the power, check. Reduce the power by 1, check. But what else do I do? Think general.
2x.
Right. And so you differentiate the inside, and just like you said, you get 2x. So what I'm going to do is tidy this up. 1/6 times 3/2 times 2. The 2 in that cancel, and the 3 in that partially cancel. And now you've got 1/2 x. X squared, take away 4 to power 1/2. Are we good so far now? Right, differentiated, made it look a bit prettier. 1 plus the derivative squared. That's essentially going to be this bit in here, right? Well, you take the 1/2 x, x squared take away 4 to the 1/2, and you square it. And if you have things that are multiplied together being squared, you can square each one separately. So 1/2 squared gets me 1/4. X squared gets me that guy. And x squared minus 4 to power 1/2, when you square it, just gets me x squared minus 4. And if I got my plus 1, so there, I'll stick it in there. So far, so good. Now, not every question, but a fair chunk of them, the majority of questions, are going to end up being perfect squares. Would you agree that doesn't look like anything useful right now? So we still got algebra to do. So what do you think I'm going to do?
Multiply it out.
Seems like a good plan. So distribute that and you get 1/4 x to the 4. Multiply that by that and I believe you get negative x squared. And then it's always a good idea to rewrite these in order of power. And that should be a 4. So 4 squared constant. Now I hope we're beginning to get used to the 3 guys becoming a perfect square situation. Not the normal kind of factoring that you would do, but nonetheless, there is a way of doing it, isn't there? Okay, 1/4 x to the 4 minus x squared plus 1. Forget about the minus x squared, right? That's going to sort itself out, but it should. Okay, where are you going? Well, it goes here and here. Okay, let's start with this one then. 1/4 x to the 4. What does that give me here? Remember what we did on Wednesday. 1/4 x to the 4. What does it give us?
Is it 1/2 x squared?
Yes. Essentially, don't you take the square root of the term, right? So 1/4 gets you 1/2, and x to the 4 will get you x squared, and x to the 8 will get you x to the 4, right? And things like that. Now, the number 1's probably the easy one, because this isn't the square root of 1. And this guy is actually him, right? It's a perfect square. That means we can now move on to finding the arc length. It's the integral from 5 to 6 of this guy. But we like perfect squares because perfect squares inside square roots cancel out. And now we're left with just finding that integral. And at this point, I'm just going to do ... because you could finish that, right? Isn't that just a power rule and plug in numbers and get some ugly answer? Yes.
Would that be -1?
Let me check. You are right. Missed that. That should be -1. Okay, let's look at y. That should be -1. Why do now that I look at it, why should that be -1 and not add 1, which is what I had a minute ago? Where's the clue? David obviously knows because he told me, but look at it. How do I know that it could, technically speaking, that could be plus or minus, and so could this be plus or minus, because you take a square root, you get both. It's very rare for that to be negative, to be honest, but this one could be. And in fact, in this case, it is. How do you know it's -1 and not +1? There is a clue here. David, tell them that.
Well, there's that negative x squared. You have to account for that.
Right, and the only way you're going to get a negative x squared is if this is -1. Right, -1 squared still gets you +1, right? It still works. But to get the middle term to work, in this case, you need -1. So well got it. Right, moving on. Could do that one. Pretty sure I did one like this, so I'm probably not going to do that one. I could do this one. They're all different in their own way. So let's just do them in just random order. Let's do 16. I want to find the arc length of this quadratic from the point -81, -9, 81 halves to +9, 81 halves. Pretty simple looking function. Horrible, horrible math. Right, let's take care of this. The point where you start, so if you imagine a half x squared, looks something like this. The point where you start is going to be here, and the point where you finish is going to be here. And we're being asked to find that length, right? Where would we start and finish? What values of x will we start and finish then in this question? Because they never gave us that information, written like that. They gave it as, here is the coordinates of where you start on the curve, and here are the coordinates of where you end on the curve. So how does that work?
Would it be from -9 to 9?
Yes. Don't you go from the x coordinate to the other x coordinate? Does the y coordinate matter? Not really for this. Just because a little thing like that could get you, because if you don't know what those numbers are, aren't you going to have a bit of a problem getting the arc length, right? Because you don't have limits of integration. Now, this one is not difficult to do, but I'm going to do it with the same technique of finding 1 + y squared. That guy gets you x. This guy's derivative squared, 1 added, gets me 1 + x squared. Now, would you agree this is not a perfect square? To have perfect square, you need 3 terms, right? A guy at the beginning, a guy in the middle, and a guy at the end. You see that? Perfect square. This is not a perfect square. The arc length is going to be the integral from -9 to 9, the square root of this guy, dx. So here's the question. What technique will we use to integrate that? So I want you to think back. Darn it, I can't remember. The end of last week or the start of this week? I'm pretty sure it was the end of last week. Can you remember a technique for integrating things like the square root of 1 + x squared?
X subs?
Correct. Any idea what the x sub for this one? Just asking a lot, but do you know?
Is it a tangent?
In this case, just one tangent. That was well done, because I was, it's been a while It's hard to sometimes see. Differentiate with theta, you get secant squared theta. Do the crossover. You get secant squared theta d theta. Now these are really long questions, so I'm only going to kind of start them off for you. So it's going to be the square root of 1 plus tan squared theta. Instead of the dx, we're going to have secant squared theta, and then we're going to have a d theta. Can anybody remember what 1 plus tan squared gets us? When you do x subs, what does 1 plus tan squared get you?
Secant squared?
Okay, so we have square root of secant squared times a secant squared. And this fella now becomes secant cubed theta. And I'm going to put a dot, dot, dot in that, because that'll at least get you to have to look back at how you would deal with a secant cubed. You know that when it's tan cubes, secant cubes, or secant tans, aren't you on the lookout for some trig identities to help you? And that is basically it. Let me check on which question that was. Anyway, that's 16, wasn't it? Guess there's something else I need to tell you. No. That's the end of that one. Okay, what have we got left? I think I'll do one more of these. Would you want 14 or 15? I don't have time for both. Which one do you want me to do?
We do 15.
Okay. Hopefully when you see that, you think chain rule. So it's going to be 1 over 1 minus x squared times the derivative of 1 minus x squared, which is 2x. And that becomes this guy. And if you do 1 plus this guy squared, you get 1 plus this ugly fraction squared. Now what's going to happen in the next few lines is some really, really ugly algebra. So I'll try and take it as slow as I can. Well, if you want to square a fraction, can't you just square the top and square the bottom? Does that seem reasonable? Are we good so far? Okay, what do you think I'm going next? Think algebra. What are we going to do next?
Factor out the fraction. I mean, multiply out the fraction.
Oh, so make that 1 minus 2x plus x squared. Thinking of that, Stefan?
Yeah, it doesn't seem right to me because if we have to put it under the square root for
You're kind of talking yourself out the right direction. What you're thinking is actually a good direction to go. All I'm going to suggest is that we hold off on factoring that out yet, because you're quite right. If I factored that out right now, it wouldn't look right because it's going to be under a square root, and that's kind of making you think I shouldn't do that. But if you do something before that and then do what you want, it'll actually come out a lot better than you think it's going to. I've got a 1 plus a fraction. What do you think I want to do before we start foiling out the bottom, which is a good idea, by the way?
multiply 1 by 1 minus x squared over 1 minus x squared so that you can add it into the top.
That is good. Does that make, keep missing my little squares in there. Does that make sense, guys? Because what we can do now is take 1 minus x squared plus 4x squared, and now it's over a 1 minus x squared.
Now we want to FOIL out the top and make it a neat, perfect square.
That's what we would hope. That's what I want. I've missed something here. There's a 2 somewhere. Where's my 2? No, my 2's here. Excuse me while I get thoroughly confused. No, that's good. Just looking at this working. Yeah, that's good. This method is right. I'm just trying to make sure I haven't screwed up somewhere. I know I have. I'm just trying to find out where.
So it would be plus x to the power of 4. Because it's
Yeah, okay,
a
we got it.
squared plus 2ab plus b squared.
That's it. I was talking myself out of it. Now,
Oh, wait, where did x squared come from? Yeah, okay. It would be 4x to the power of 4.
there we go. Yeah, I was talking myself out of the game here. This thing, I was trying to foil this in my head and screwing up badly. I probably should have just done an extra line of work and it would have saved me all the grief. If you take 1 minus x squared, you get a 1. Eventually, you get a negative 2x squared plus an x to the 4. And then you've got over here 4x squared, which means if you write it in order and combine them, you get this guy. Agreed? X to the 4, that guy and that guy get you plus 2x squared now, and a 1. I like to put them in order of powers, so I rearrange the order. That top guy is a perfect square.
X squared plus 1 squared.
There. Surprising that it actually became, a perfect square, didn't it? Didn't look like it was going to be. Told you it was some horrible algebra. So the arc length is going to be the integral from 0 to 1/8, the square root of this guy. But that guy can be simplified. And now we're there. I wish I could say, oh, well, 2 lines later, you're going to have the answer. That darn question has a whole load of stuff to do, but I'm not going to finish it. I'm just going to tell you what the stuff that you need to do. You're going to have to look up rational integrals, right? How to integrate rational functions. This guy here, you're going to divide them, or create a version of it, and you are going to get a number which I'm going to pretend is 2 plus 1 over 1 minus x squared. That's not what it's going to be, because I want you to find out what it is going to be. But it's going to look like that kind of shape. You're then going to take this guy and call him a 1 minus x, 1 plus x dx. What's going to happen with this fraction? By the way, it won't be plus 1. It's much more likely to be negative 1. But what is going to happen to this guy? Do you see a method that we would use to integrate this guy?
Cover up method.
And it'd be the cover up method. So can you see that question is going to be a bit of a stinker? I mean, it's going to take you a long time to do.
I mean, after the cover up method, it doesn't look like too complicated of an answer. And then
Yeah, I
just
mean,
on your head from there.
you're still going to have to play about with 1/8 and things to make it look pretty. So
Uh,
there's, even when you're finished, there's still some style points where you have to work with 9/8 and things like that and make them combine with other logs. And, you know, the final answer ends up being, well, I'm looking at the answer on website. The final answer ends up being the natural log in 9/7 minus an 8, at least for my question. Okay, let's look at these guys now. The good news is that there is nothing new. This is basically, you're just taking a function that works on this direction. So there's C, and up here is D. And this function is going to be called x equals g of y. And we are just finding what the length of the curve is. Arc length. So let's start with this one. I'm pretty sure it's going to be a perfect square. 1/8 y to the 4 plus 1/4 y to the negative 2. And by the way, that's a y. And it looks like that. If you go back and look at Wednesday, I bet at bottom dollar we done one that looked very similar to that. The only difference is that the one we did would be y equals, you know, something like an 8. Right. Right, it looked like that. Mathematically, these two are equivalent. They're virtually identical in how you approach. So we're going to differentiate this guy. So I'm going to use that notation for the derivative, because when the x's and y's switch place, it's kind of hard to understand what's going on. So multiply by the power, reduce the power by 1. Multiply by the power, reduce the power by 1. 1 plus the derivative squared is 1 plus this guy squared. And you're going to trust me on this one. If you FOIL this guy out, you get 1/4 y to the 6. You get negative a quarter, negative a quarter, and a plus 1/2 y to the negative 6. When you combine all these fractions and numbers together, you get this guy. M squared. And would you agree that's a classic shape for a perfect square? Agreed? 3 terms, classic shape for a perfect square. Okay. Since they are in order, which is nice, what's the first term going to be where my finger is pointing? What do I write here?
Got 1/2 y cubed.
And this is plus, you can tell with the middle, it's everybody's plus. And what goes at the end then?
1/2 y to the negative 3rd power.
Is this perfect square piece of algebra becoming a bit easier now that you've seen about 5 or 6 of them? They all, you know, you kind of do the same thing, right? So far, so good. So what we'll do now is get the arc length. So it's going to be the integral from 1 to 3, the square root of this guy. dy. So it's going to be the integral from 1 to 3 of 1/2 y cubed plus 1/2 y to negative 3. Let's take this one a little bit further. Power rule, add 1 to the power, divide by the new power. Add 1 to the power and divide by the new power. And evaluate from y equals 1 to y equals 3. But since we want a nice looking answer, a style point answer, I strongly suggest that whenever you have negative powers, that you return them to fractions. And whenever you have fractional powers, you turn them into radicals, right? You turn them into square roots and cube root guys. Because if you do that, there's a better chance that you'll get the answer to look pretty at the end. So I'm going to plug in 3. So it's going to be 1/8 3 to the power of 4 over 1 times 4, 3 squared. Take away 1/8, 1 to the power of 4 is just an 1/8. Take away a quarter. And this is going to be 81/8 and 1/36. Subtract 1/8, add 1/4. And I think at this point, don't we all go for the calculator? So let's see what that one is. I have an 81/8, take away a 1/36, take away a 1/8, add a 1/4. And horrible decimal. But then you press the math button, choice 1, and turn your answer into a fraction. And 92/9. Looking good. Our first arc length for functions written in terms of y. Now, if I'd done this question as 1/8 x to the 4 minus 1/4 x to the -2, and the x's also happen to be between 1 and 3, you shouldn't be surprised that the answer is still 92/9. It makes sense. The variable here is really just a dummy variable. It's a placeholder for a relationship. I could have called this y equals 1/8 t to the 4 plus 1/4 t to the -2 and t from 1 to 3, and I would still have got the right answer. Right. The name of the variable is not that variable. Let's do 12, or at least a version of it. Okay, go to differentiate this guy. Well, I like e to the y, so that's e to the y, and differentiate this. Don't forget the negative, almost did. Get that? One plus the derivative squared becomes 1 plus this guy squared. And you're going to trust me on this one. When you FOIL it, e to the y times e to the y gets you e to the 2y. You get a -1/4, then another -1/4. And when you take this guy and multiply him by itself, you get plus 1/16 e to the -2y. And when you combine all the numbers, you get the classic 3 terms. Okay, anybody feel brave enough to factor that guy as a perfect square?
E to the y
Correct.
and 1. Is it 1/4
Yes.
e to the -y?
Yes. And a plus because of the middle term. Are we good? if you square root something, isn't one way of thinking a square root is halving its power? So half of 2y gets you y. Half of negative 2y gets you negative 1y. And when it's numbers, square roots are a bit more obvious. But the square root of 1/16 is 1/4. So essentially, I took the square root of the first term to get this guy, and the square root of the last term to get this guy. So our arc length is going to be the integral from 0 to 4, the square root of this guy plus this guy squared. And that gets us, because of the square root interaction, we get that guy. Let's just dot that one. Would you say that was a pretty straightforward integral? Nothing too weird going on. Any questions so far? Are we good? Law algebra, right? A lot of making things perfect squares or playing about with fractions and trying to make them into a single fraction. Our final question then. Okay. Before we do this one, I had an email from a student who was allegedly in my class. But the question they asked kind of proved to me that they probably weren't, which makes me feel that that particular student turned up, said their last name, and then left. Now I can tell David's here because I can see him. So I know it's not David, and I'm not mentioning names. So we're going to change our attendance policy. The time right now is 8:41. So say your last name right now, even if you've done it before. And if you're here, you are hearing me tell you that. And if you aren't here, I will know that you're likely one of those people that I believe are not coming to class at all. So say your last name right now.
I'm sorry about Wednesday. I got called away from the computer and it stayed on Zoom. I kind of forgot about it.
It happens.
Yeah, I'm also like sorry about this on the Wednesday. Because the time changed maybe in the state. So my class has changed to 12 a.m. So I'm pretty like sleepy on Wednesday, so I lost my class. Sorry about that.
It's okay. I'm just making sure that people get what participation they have for participating. So that's it. So if you haven't put your name between A41 and A42, you're not here. Okay, let's get started. Last question. Oh God, that's ugly, isn't it? Why am I turning a perfectly pretty square root of y into a rather ugly y to the power of half? Why am I doing that?
Easier to manipulate.
Isn't it going to be easier to distribute as a fractional power? So multiply this and you get 1/3 y to the 3/2 and multiply these together and you get that guy. Now, fractional powers are pretty ugly and fractional powers tend to not be the final answer, but you still need them, don't you, if you want to differentiate. So sometimes you have to turn things into fractional powers to be able to differentiate and integrate and all that good stuff. But once they've done that, you tend to get back into the square root world because that's going to be where the style points, where the nice answers live. So we're going to differentiate this. Multiply by the power. and reduce it by 1, multiply by the power, and reduce it by 1. You got that guy? And then it is take this guy and square it and add it to 1. Just like I said the last few, I'm doing a FOIL here. You're just going to have to trust me. When you multiply this guy by himself, you get 1/4 y. When you multiply these two together, you get -1/4. And you do it the other way, you get another -1/4. And when you multiply this guy by himself, you get +1 y to the -1. And now we have 1/4 y. 2 of these, and that gives you +1/2. And then at the end, you've got 1/4 y to -1. It's got 3 terms to it.
Wouldn't -1/4 be -1/2?
Yeah, and then add that one gets +1/2, yes.
Oh,
Right?
Yeah.
You're right, -1/4 is -1/2, but we've also
I
added
missed the one. Sorry about that.
not a
Thank
problem.
you.
Right, what are you going to do here? Well, it's 3 guys, right? So it's a perfect square. And sometimes you have just got to trust the method, because you could look at that and talk yourself out and say, nah, that's not a perfect square, right? Perfect square have y and 4s in them or something, right? I've never seen a perfect square with just a y and a -1, but it is a perfect square. And the trick for getting perfect squares is, don't you take the square root of each of the terms at the beginning and at the end. Okay, let's look at this fella. Right, square root of 1/4 y would be 1/2 y to the half. Agreed? Isn't y just y to the 1, so half its power is 1/2. So this guy over here, plus, because that's plus, 1/2 y to -1/2. So it is a perfect square. Would you agree it's kind of weird looking, a little different from a typical one? But to be a perfect square, at least in these questions, don't you just need to have 3 terms in order? And you take the square root of the first guy and the square root of the last guy. And just the way these questions work, this guy, if you foiled him out, I guarantee is him, right? So it is a perfect square. So our arc length is going to be the integral from 16 to 25, the square root of this guy squared dy. And that means that the square and the square root kind of kill each other off. And you're now looking at that guy. Let's take it a little bit further. Add 1 to the power and divide by the new power. So it's really multiplying by 2/3, so you get 1/3. Add 1 to the power. And then divide by the new power, you just get 1. And evaluate it at 16 and at 25. Do some style points on it. This fella is the square root of y cubed. And this guy is the square root of y. And the reason I want to do it that way is we want our answers to look nice. Square roots are nice to deal with, especially when numbers are involved. So it's 1/3 the square root of 25 cubed plus the square root of 25. Take away 1/3 square root of 16 cubed plus the square root of 16. Now, I know this number here looks ridiculous, but actually it's just 125. So it's 1/3, 125. This one's just 5. This guy here is 64, so it's 1/3 times 64 plus 4. See, it came out quite nice. So it's 125 thirds plus a 5, take away 64 thirds, take away a 4. I could probably do that in my head, but I'm not going to risk it. 125 thirds, add a 5, take away 64 thirds, take away 4. And the answer, whoops, when you turn it into fraction, is 64 thirds. Perfect timing, pretty much. That is the end of arc length. Any questions before we finish up? Right. Have a nice day, everybody. I will see you on Monday now. God, this week's shot by, hasn't it?
I feel like that's going to be the theme for November.
So again, James,
I feel like that's going to be the theme for November.
what, that it shoots by?
Yeah.
Oh, it is going to shoot by. We have a full week next week, thank goodness. But the week after that is going to be ridiculous. Monday's going to be the test. Tuesday, you are not going to come to class. I am going to make a video of what it would be like if you were in class, because I know some of you are going to be likely to be getting ready for Thanksgiving or traveling to family or so on. So I'm putting Tuesday will not be a physical class. You'll get attendance. I'll make a video, I'll be here doing a video, just you won't be, right? And then it's Wednesday, Thursday, Friday, you're off. So basically that week consists of a test. And then you come back the next week and we're done. That's how little time they've got. Shoot. We've learned some cool stuff right enough, haven't we? So we've still got some cool stuff to go. Okay, bye-bye, everybody. I don't need attendance now because of what we did earlier. And I shall see you on Monday.
Professor,
Yes, Koji.
I have a question on section 7.8, about question 11.
Can you tell me the question, what it is?
Yes, it's integral from negative infinity to positive infinity, x power of 5 over x power to 6 plus 1.
That one?
Yes.
Okay. Because it's got two infinities, the first thing you're going to have to do is split it. I would split it at 0. We good so far?
Yeah.
Now, it doesn't matter which one I pick because the answer is going to be at diverges, but let's say I pick this one, right?
Right.
It's going to be the limit as t tends to infinity of 0 to t of x to the 5 over x to the 6 plus 1, right? Nothing too miraculous here. Do you recognize the technique that you're going to use to integrate this fraction?
Oh, it's
a pretty, you're going to, and isn't the u sub going to be u to the 6 plus 1?
Right.
Right, I'll do it over here because I don't have enough room to squeeze it in here. So the u sub is x to the 6 plus 1. Its derivative with respect to x is that guy. The crossover gives me this guy. And then you divide by 6x to the 5 to get that guy. So it's now going to be the limit as t tends to infinity. I omit the limits integration now because technically we're changing variable. And it looks like that. So far, so good.
Yep.
It's now going to be the limit as t tends to infinity. The x to the 5s cancel, and I like to write it kind of separate like that. So it's 1/6 this guy. Now that tells me that the answer is going to be the limit as t tends to infinity of 1/6 the natural log of u, which when we convert it back into the x's becomes 1/6 the natural log of x to the 6 plus 1. And then we can evaluate it at 0 and at t. So that becomes the limit as t tends to infinity of 1/6 the natural log of t to the 6 plus 1. Take away 1/6, well, it's just really the natural log of 1, because 0 to 6 still 0.
Right.
Right, pretty much ready to brute force it then. 1/6 the natural log of infinity to the power of 6 is still infinity. Take away 0. And infinity to the 6 plus 1 is still infinity. And the log of infinity is still infinity. And so the answer is infinite, and so it diverges. And I don't need to do the other one because I don't care. If one bit's broke, the whole thing's broke.
Right. I got it. Thank you.
Okay. Any other question, guys, before we call this a day?
I'm good, I think.
We are good. Right, I will see you all on Monday. Have a nice weekend.
Thank
Thank you.
you. You too.
You too. Bye-bye.